Hello. Hello and welcome. So let's carry on. Today's topic is analysis of functions. It is a big topic. However, I have to say it's a little bit of an old school topic because the main aim is to understand the behavior of a function. But in today's world, you can plot any function with a graph in 2 seconds. This wasn't an option when I was your age. That well, we just didn't have that. Like today, you just take Desmos and it will draw any graph for you. However, I think that it is incredibly important to be able to do this because well, this helps the general effort to say, and the general effort of COMPOS is to teach you to problem solve. Because you won't, in life, you won't be tested on your math skill. You won't be tested on your knowledge of the exponential function. In life, you will be tested on your problem solving abilities. That's what we're trying to develop at COMPOS. Okay, so let's get to it. Let's talk about odd and even functions. You might have heard about odd and even functions. So here are some examples of functions. Some of them are odd, some of them are even, some of them are neither. Let's write down the definition and how to figure out whether a function is odd or even. So a function is odd if two things are true. First, the domain is symmetrical. And secondly, if f minus x is equal to minus f of x. So f of x is odd. F of x is even if a similar statement to, you know what, I'll copy that and just make an adjustment. So copy, the domain is symmetrical, and f of x is like this, without the minus. Okay, so let's test the three functions above, whether they are odd, even, or neither. Okay. So first we test the domain. Domain, what's the domain of this function? Well, what can x not be equal to? Are there any limitations on x? Yes. So x is not equal to 0. So x is not equal to 0. So is it symmetrical? Is the domain symmetrical? Yeah, it is. So tick. First test has passed. Second, we find f of minus x. So we substitute minus x, and that's minus x to the power 5 divided 2 minus x. And well, if you know your maths, this can be written as x to the 5, which is 2x, which is exactly f of x. So that means it's an even function. Even function. Okay, let's do the second one. Okay, so the domain well, x is not equal to 3. It's not symmetrical, so it can't be an odd or even function by definition. And second one, third one, the same. X is not equal to 0, and x is not equal to -4. Therefore, it's not an odd and even function. But let's test this second statement. Let's regardless of that, let's test if they if we have anything. So f of minus x is going to be 3 multiplied by minus x squared minus x cubed, 6 minus 2 minus x, and that's x minus x squared is x squared, so 3x squared plus x cubed, and 6 plus 2x. Well, I have to say this is not equal to f of x, and this is not equal to minus f of x, so it's neither. But we already knew that from the first statement, from the first test. The domain is symmetrical across the real numbers. So, for example, this is 0. Let's say x is not equal to 3, x is not equal to -3. So if x is not equal to 3, then it has to not equal to -3 as well to be symmetrical. So all the points where it doesn't exist should be symmetrical. How do you work out the domain? You just look at the what are the limitations? What are the limitations on x? So here, the only limitation is division by 0. So you can't divide by 0. That means x cannot equal to 3. Here, x cannot equal to 0 and x cannot equal to -4, because if x is 0 or -4, the denominator is 0. Okay, so that's not symmetrical, therefore that's not. But interestingly, if I do f of minus x, if I substitute 2 multiplied by minus x plus 8 over x minus x squared plus 4 times minus x, so that's a minus 2x plus 8, which is x squared minus 4x. Now it doesn't look like that, but I can actually I can do this here as well. Look, okay, I could simplify this and just say 2x plus 4, and then x plus 4, and x plus 4 cancels, and I get 2 over x. Now for this one, I have minus 2 x minus 4, and then I have x minus 4. X minus 4 cancels, and I get minus 2 over x. So if it weren't for the domain, so that is equal to minus f of x. So if it weren't for the non-symmetrical domain, this would be a this would be an odd function. We can make it odd. To make it odd, we just need to make it exist at -4. Okay. And it's going to be at -4. This is going to be -1/2. So in order to make it odd, we need to modify it. We have to say that y is equal to 2x plus 8 over x squared plus 4x if x is not equal to -4, and it's equal to -1/2 if x is -4. And this function is indeed odd. So this function is neither, because its domain is not symmetrical. But because f minus x is equal to minus f of x, by doing this, we make the domain symmetrical. And therefore, it becomes odd. Let's see if we can sketch that using Desmos. So y is equal to 2x plus 8 over, oh, it doesn't work like that, doesn't like that. So 2 plus 8 x squared plus 4x. So you can see this looks like an odd function. However, if I go to point -4, it's undefined. It's undefined at that point. Whereas here, it's not undefined. So what I need to do is just define the function at that point. So x not equal. Does it have not equal? Less than 4 or -4. X -4 and doesn't like that. Okay, but I hope you got the gist. Okay, this function, if I simplify this, that would be x squared 3 minus x over 2 3 minus x. So 3 minus x cancels and let's get x squared over 2. And this function, the f minus 1, you can also take x squared out, 3 plus x and x 2, 3 plus x. So these cancels and it is x squared over 2. So if it weren't for the domain, it would be odd. Now, even functions are symmetrical over the line, over the y-axis. So the y-axis is a line of symmetry for this function. Therefore, this is an even function. Does that make sense? So we say f of minus x is the same as f of x. So f of minus x is here, and f of plus x is here. So they are the same. They have to be. Okay, number five, is it even or odd? Number 5 is even, yes. What? Number 10 is even. Number 11 is even. So an even function, the positive and the negative value give you the same y. Yeah, does that make sense, Maria? Yeah. Okay. And somebody just joined, Olutimi. Hopefully you've managed to catch up. So then let's find the odd. This is an odd function because it's symmetrical. It has a rotational symmetry of order 2. So all odd functions have rotational symmetry. So how does that work? Well, this is x, and this is f of x. F of x. And minus x is on the opposite side. It's symmetrical to x. And it's minus f of x. And remember, I said it has to be symmetrical, because if it exists on the right, it has to exist on the left. Because if the point exists on the right but doesn't exist on the left, then this doesn't make any sense. Okay? So that's why it has to be symmetrical. So here, this is an odd function, or judging from the graph. This is neither. This is neither. This is odd. This is neither. This is neither. And this is odd. Okay. Monotonic functions. A monotonic function is a function that is always increasing or always decreasing. An example would be the square root. Y equals square root of x. Y equals square root of x. It's always increasing. It looks like this. Now, the definition, the function is monotonic increasing. Increasing if for any, this is a symbol for any x1 and x2, if x2 is greater than x1, then f of x2 greater than f of x1. That's a monotonic increasing. This is strictly monotonic increasing. Strictly monotonic decreasing. Decreasing. If for any x1, x2, if x2 is greater than x1, then f of x2 is less than f of x1. So a monotonic increasing function, well, basically it says if x2 is bigger than x1, then f2 is bigger than x1. So this is x1, this is x2, and this is f of x1, and this is f of x2. So if x2 is greater than x1, then f of x2 is greater than f of x1. So hopefully that makes sense. It's a decreasing function. Decreasing function if for any 2 points, the bigger x will give you a smaller y. So x2, x1, this is f of x1, and this is f of x2. And we have f of x2 is less than f of x1. In simple words, the function is going down, sloping downwards. This could also be written as, simply put, is the derivative of the function is positive, and it's decreasing if the derivative is negative. If it's neither decreasing nor increasing, the derivative is positive. 0, sorry. So let's see. The task is to determine whether this function is monotonic. Determine whether the function is monotonic. All right, so what do we need to do? Well, we can either try to find f of x1 minus f of x2, but that's going to be a big hassle. So what I'm going to do is I'm going to differentiate. And before I differentiate, I'm going to simplify this and say 2x cubed minus 15x squared plus 36x to the power 1/2. And now I can differentiate it using the chain rule. So I find the derivative, and that would be 1/2 multiplied by 2x cubed minus 15x squared plus 36x to the power minus 1/2, because that's how differentiation works, multiplied by the derivative of this thing, multiplied by 6x squared minus 30x plus 36. I need to simplify this. So 1/2, I can take 6 out from here. So it's going to be 6, and 6 over 2 is 3. So 3, open bracket, x squared minus 5x plus 6 divided by the square root of 2x cubed minus 15x squared plus 36x. Now we know that the square root can only be positive, non-negative. Okay, so we have to exclude the domain. Do we need to find the domain? I'm afraid we might just need to find the domain. Okay, to find the domain, we say, okay, what are the limitations? Well, we can't have a square root of a negative number. So to find the domain, we have to say 2x cubed minus 15x squared plus 36 must be greater or equal 0. X. So I take 2, I can't take 2. So x I take out, 2x squared minus 15x plus 36, and that's greater or equal 0. I can factorize this. Does it factorize? 3, 2, minus 15, 36. Oh, it doesn't factorize. So this doesn't factorize. That means it's always positive. So this is positive when x is positive. Okay, so x has to be greater or equal to 0. Okay, x has to be greater or equal to 0. That's the domain. Because this thing is positive always. Okay, now we have this. We know that this is positive when x is positive. So x has to be greater or equal to 0. Of course, if x is 0, this is division by 0, so x is greater than 0. We can factorize the top. It's going to be 3x minus 2, x minus 3. And here we have square root of x 2x squared minus 15x plus 36. Okay, so we need to work out when the derivative is positive or negative. Well, we can clearly see that the function only exists if x is positive. Okay, so x is positive. Here, we need to solve a quadratic inequality. So let's say we want to find where it's positive. Quadratic inequality, and so it would look like this because we have two solutions. So 2 and 3 and 0, of course, and it only exists if x has to be greater or equal to 0. So it's positive when it's here, and it's negative here. So the first derivative is positive when x is less than 2 and greater than 0, or when x is greater than 3. And f, this first derivative, is negative when x is between 3 and 2. That means the function is increasing from 0 to 2 and from 3 to plus infinity. So the answer, increasing for x belongs to from 0 to 2 or from 3 to plus infinity. Decreasing when x between 2 and 3. All right, let's check. 2x cubed y equals square root 2x cubed minus 15x squared plus 36x. Ooh, it does look like we were right. So this is 2, this is 3. So it's increasing from 0 to 2, decreasing from 2 to 3, and increasing from 3 to infinity. Does that make sense? Okay. So you can test. So between 0 and 2, it's positive. Between 2 and 3, it's negative. Between 3 and infinity, it's positive. fx is x cubed minus ax squared plus 3ax plus 1 is monotonic. Find the possible values of a. So this is a cubic graph, and you can see that a does not affect the position of the cube. So it's going to be, well, it's going to be like this. It's a cubic graph which is increasing. So when we say monotonic, monotonic increasing, of course. And let's so find the Poisson values of A. Okay. So for this to be monotonic increasing, that means f dash x has to be greater than 0 for all values of x. So let's find the derivative. So f dash x is equal to 3x squared minus 2ax plus 3a. And that has to be always positive. Now, what does it mean when a quadratic is always positive? A quadratic is always positive if the discriminant is less than 0. So a quadratic is always positive if the discriminant is less than 0 and the leading coefficient is greater than 0, of course. Okay, so we find the discriminant. The discriminant is equal to b squared minus 4ac. So b squared minus 4ac, which is minus 2a squared minus 4 times 3 times 3a. And that has to be negative. So that's 4a squared minus 12 times 3, 36a, less than 0. Take 4a out. So a minus 9, less than 0. And it's less than 0, so that's 0. And 9. So it's negative here. Okay. It's negative between 0 and 9. So a is less than 9, is 0. Or as I prefer to write it, a belongs to the set from 0 to 9. So when a is between 0 and 9, the function is always increasing. Answer. If a is from 0 to 9, f of x is increasing. Okay, let's check again. So it's 3x cubed. Desmos is amazing with those things. Y equals x cubed minus ax squared plus 3ax plus 1. And we need to add a slider. Okay, and let's make a better range. So minus 5 to 15. Okay. So you see when a is minus 5, the function is not monotonic. Now if I drag a, if I increase a, so when a becomes 0, it becomes monotonic. If I increase a, I keep increasing a, and now it stops being monotonic again. Right. So between 0 and 9, which is here, the function is monotonic. and then it stops being monotonic. So that's quite an interesting one. Okay. Problem 4. Find critical points, sketch the graph. So a critical point is where the derivative is 0. And sketch the graph. So first, we start by finding the domain. So what are the limitations on x? Who can tell me? Who can help me with that? X has to be greater or equal to 0, of course, because you can't have a root of a negative number. Okay, good. And now let's find the derivative. So that would be 16x minus 4. So it's 4 times a half times x to the power minus a half. So that would be 16x minus 2 over root x. We want to find where this is 0. So we solve that. So 16x times root x equals 2. X root x equals 1/8. So x to the power 3 over 2 equals 1/8. So x to the power 1/2 is equal to 1/2. So x is equal to 1/4. All right. 1/4 is a stationary point. Stationary point. So we need to find y of 1/4. So y of 1/4, that's 8 multiplied by 1/16 minus 4 multiplied by square root of 1/4. So that's 1/2 minus 4 over 2. So that's minus 3 over 2. So I suspect that this would be a minimum point. Okay. Now, so stationary point is either a maximum or a minimum or a point of inflection, of course. I found the y coordinate. Okay, so let's begin sketching the graph. So what do we know? Well, we know that when x is 0, y is 0. Okay, that's the first point. Secondly, we know that when x is a quarter, so let's make this a quarter, and this is minus 3 over 2. So 1/4 minus 3 over 2. Yeah, so if it's bigger here, it's stationary here. I suspect this is going to be a point of minimum. How do I check that it is a point of minimum? Well, there are several ways. I can find y of slightly less than 1/4. So let's say 1/4 minus a small number, minus epsilon. So basically, I check the values to the left and to the right of this point. Or I can find the second derivative. Would that be useful? Yeah, I think that would be useful. The interesting thing about the second derivative, let's talk about the second derivative briefly here. Second derivative. Second derivative. So if the second derivative is positive, then the function is convex. So that means it's a convex function. If the second derivative is less than 0, the function is concave. Concave. What does a convex function mean? Well, first of all, if you draw a chord, the chord would be above the line. Whereas here, the chord would be below the line. So if you have a stationary point and a function is convex, then it's a minimum point. And if you have a stationary point and the function is concave, this is a maximum. Okay. So you have a maximum point if the first derivative is 0 and the second derivative is negative. You have a minimum point if the first derivative is 0 and the second derivative is positive. So minimum point, max. So that's a very useful tool to use, the second derivative. So you can identify whether the function is convex or concave. So let's do this at point 1/4, second derivative. Well, y dash dash. So you can differentiate that. So that would be 16 minus 2 times minus 1/2 multiplied by x to the power minus 3/2. So that is 16 plus plus x to the power minus 3/2, which is 16 plus 1 over x root x. But because we know that x is always positive, that means the second derivative is always positive when x is positive. So the second derivative is always positive. That means that the function, it's always convex. Always convex. And that means that it is a minimum point. Okay, so that is a minimum point. Then we want to find the zeros. We can do zeros. The zeros of a function, so we make it 0, so that's x equals 0, of course. That's for the first 0. And another 0 is when this thing is 0, so 8x squared minus equals 4 root x. So that's 2 x to the power 3/2 is equal to 1. X 3/2 equals 1/2. X cubed is 1/4. X is cube root of 1/4. That's another 0. That's another 0. So that's somewhere here. Cube root of 1/4. And here we are. So it's going to go like this. Like this. And because it's always concave, it will go like this. So that's what we did. We found the critical points, which is 1/4. We found the y value, and we've drawn a graph. Problem 5. Find critical points, sketch the graph. So very similar task. So we have the domain. So there are no limitations on x. So domain x is any real number. Now we want to find the zeros. And that x plus cube root of x minus 1 is 0. X is equal to minus cube root of x minus 1 I cube. So x cubed equals minus x plus 1, x cubed plus x minus 1 equals 0. It's not easy, so I'm going to use technology. I'm going to use my calculator to do this. So that's going to be 1, 0, 1, minus 1. I've got x is approximately 0.682. That's one of the roots. Doesn't give me the exact value. Okay, so that's a 0. Good to know. Then what can I say? Let's find the first derivative, y. It's going to be 1 plus 1/3 x minus 1 to the power minus 2/3. So 1 plus 1 over 3 cube root of x minus 1 squared. And I can immediately say that this is always positive because it's a square. It's x minus 1 squared. So it's always positive. It's greater than 0. So the function is monotonic increasing. Monotonic increasing. And it's going to be quite a boring function. So you can see that it becomes x plus minus 1. So it has a 0 at, it's equal to minus 1. It has a y-intercept of minus 1. And it has a 0 at about here. So I'm suspecting the function would go something like this, bending slightly up and bending slightly down here. Okay, x, y. By the way, this is a very common task on a university exam, well, university interview. So for example, on Oxbridge interview, they always ask you to draw a graph of something. So that's one of the things that you really need to have solid understanding of. So x plus cube root. So y equals x plus cube root x minus 1 to the power minus 1/3. Oh wow. X minus 1 to 1/3. Oh, it's plus 1/3. Ooh. I was scared. Okay, yeah. Something like this. I did not foresee this. Did not notice that this is a point where the derivative is infinite. This is where the derivative doesn't exist. Of course, at x equals 1, this is a very peculiar point. At x equals 1, the derivative becomes infinite, or tends to infinity. At x close to 1, it goes to plus infinity. So yes, so when it is 1, it's going to go infinite, and then again like this. So slightly different from what I expected. And it's bending down. Interestingly, it is bending down. So I was quite off. Okay, so bending down. Like this. We call this is called a point of inflection. Inflection point. This is a point where the second derivative is 0. Well, in this particular case, the first derivative doesn't exist. Okay, that's quite cool. Now I want to talk about periodic functions. This is a periodic function. A periodic function is a function that repeats itself. Effectively, that means if we have f of x plus a is equal to f of x for any x, that means it's a periodic function where a is the period. Okay. So we know for sure that cosine is periodic. But if cosine is periodic, that means our cos of cos will always repeat itself. Right? It's like, imagine cos for just cos going 1, 2, 3, 1, 2, 3, 1, 2, 3. And then arc cos of cos is going to be arc cos 1, arc cos 1, arc cos 2, arc cos 3, arc cos 1, arc cos 2, arc cos 3. It will also be periodic. It makes sense. Of course, cosine is not 1, 2, 3, 1, 2, 3, but I hope you understood the general idea. So we want to sketch that. We know that cosine x has a period 2 pi. So we do expect arc cos to also have a period of 2 pi. Cos x is an even function. So we expect arc cos of cos also to be even. So y is even as well. Okay. Right. So let's just recap. What is arc cos? Arc cos x. So f x equals arc cos x. So it's a function. The domain of that function is -1 to 1. When x is zero, well, arc cos 0 is 1. And arc cos 0 is pi over 2. So pi over 2. And arc cos -1 is pi. So the graph goes like this. This is arc cos -1. Okay. Now, so we have y equals cos x. No, that's y. F of x equals cos x. Cos x looks like this. Zero. So it's 1. At pi over 2 is 0. At pi is minus 1. So it's going to go like this. X. And of course, 1, 2, 3. This is pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. So we are kind of interested to sketch this graph on from 0 to pi over 2 and then just repeat it, because it's going to be periodic and it's going to be symmetrical. Okay. So this is y equals arc cos x. Well, let's start with 0. Cos 0 is 1. So arc cos 1 is 0. So we start from 0. Interesting. We start from 0. So as we increase, as cosine increases, so as x increases, cosine decreases. Okay, so as x increases, cosine decreases. So arc cos. So arc cos has a range from 0 to pi. So when we're expecting this to also have a range from 0 to pi. Okay. So it's going to go up from 0 to pi. 0 to pi. So range 0 to pi. Domain x is any real number. So as x is increasing, cosine is decreasing. And as cosine is decreasing, arc cos is increasing. So it's going to go like this. So we know that arc cos of cos, we know that f minus 1 of f of x is just x. So that means arc cos of cos x must be just x. So from 0 to pi, it must be increasing, just linearly, like this. As we reach pi, cosine reaches its minimum value at pi, and now it starts to increase. But it increases gradually, so cosine, so it kind of walk back from minus 1 to 1. That means we walk from pi back to 0. Back to 0. So that's 2 pi. And you can check, you can use some points and you can check that it actually does hold. So for example, if you take pi over 6. R cos pi over 6, that's going to be pi over 6. Arc cos pi over 3 is going to be pi over 3. So pi over 3, pi over 6, and pi over 6. And this is pi over 3. Now, if you do R cos 4 pi over 3, that would be pi over 3. So that would be here. So 4 pi over 3 would give you pi over 3 as well. And 5 pi over 6, it doesn't make any sense. That's not 5 pi over 6. And so that's 4 pi over 3. 4 pi over 3 is 4 pi over 3. And 7 pi over 3. 7 pi over 3 is going to be 4 pi over 3. Yes. And arc cos it's 11 pi over 3. What? Sorry, I'm messed up. 7 pi over 3. 9 pi over 3. 9 pi over 3. No, sorry, I got lost. So that's pi. That's pi over 3. This is 4 pi over 3. And this is 5 pi. That must be 11 pi over 6. 11 pi over 6. So cos pi over 3 is pi over 3. Cos 4 pi over 3 is pi over 3. Over 3. And arc cos 11 pi over 6, that's going to be pi over 6. Sorry. And you will see that the graph goes like this. But this is a periodic graph. A periodic graph, that means it repeats itself. So it's going to go like this. Okay. So quite a tough one, but let's see if we were correct. Arc cos x. Oh, beautiful. This is a beautiful graph. Okay. All right, moving on. Finally, we get to the point where we need to investigate the function and sketch the graph. I'm going to show you how I do it normally. You don't have to do it the same way. You want to find the zeros, you want to find the y-intercept, you want to find the asymptotes, you want to find the stationary points in monotonic intervals, you want to find the inflection points, you want to find the domain and range. You don't have to do it in that order. So, domain. Domain is x not equal to 1. Range. Can we find the range? I don't think we can find the range straight away, so range is question mark. Question mark. I can't see an easy way to find the range because this is positive. This could be anything. So yeah. All right. So intercept. That's when x is 0. So that's y of 0 is 0 plus 8. 1 minus 0, so that's 8. So 0, 8 is the y-intercept. That's useful. Zeros. Well, there's none, because x squared plus 8 is never 0. So no zeros. Ooh, interesting. So no zeros. Asymptotes. Well, x equals 1 is a vertical asymptote. Okay. Now, I can find the slant asymptotes. To find the slant asymptotes, I want to simplify this. So I can write y equals x squared plus 8 divided by, well, x minus 1. Well, let's do it like this, minus x minus 8. Okay. I kind of want to divide, I want to simplify this fraction. To do this, I do something quite unusual, I'd say. I do minus x squared. I want to have the same thing. I want to be able to simplify. I want to have x minus 1. So it's going to be plus x. And then I do minus x to compensate. Minus 8. X minus 1. So why did I do this? You will see. It's quite clever. Minus x squared plus x. I'm going to break it down into two fractions. Minus 1 minus plus minus x minus 8 over x minus 1. So this can be written as minus x minus 1 divided by x minus 1. So x minus 1 cancels. So I get minus x plus. Now I'm going to repeat that. I'm going to write minus x plus 1 minus 9. Because 1 minus 9 is minus 8. So x minus 1. So I've simplified this, and I now can write minus x plus minus 1 minus 9 over x minus 1. Okay. Don't worry if you don't fully get it. This is how I find the slant asymptote. So as x tends to infinity, this thing tends to 0. Therefore, my graph becomes approximately this. So once again, y can be written as minus x minus 1 minus 9 over x minus 1. So as x tends to infinity, y is approximately minus x minus 1, because this thing becomes really small. So we kind of ignore it because it goes to 0. So this is what we call a slant asymptote. Slant asymptote. Okay, that's interesting. So what do we have so far? We have, I think I can only do one graph today, so apologies for that. So I have a vertical asymptote at x equals 1. I have a slant asymptote minus x minus 1, so that's going to go like this. So that's minus 1, 1, minus 1. So that's a slant asymptote. X, y. Now I want to find the minimums and maximums, so I want to differentiate. So I want to find y dash derivative. So I use the quotient rule here. So it's going to be 2x multiplied by 1 minus x minus x squared plus 8 multiplied by minus 1 divided by 1 minus x squared. So that is 2x minus 2x squared minus plus x squared plus 8 divided by 1 minus x squared, which is minus x squared plus 2x plus 8 over 1 minus x squared. And so I want to know where this is 0, right? So minus 1, 2, 8. Oh, it's the wrong one. 3 minus 1, 2, 8, 4, and minus 2. So x equals 4 and x equals minus 2. These are stationary points. And 2 minus 2, so that's here. Minus 2 and 4, 1, 2, 3, 4. Okay, so 4. And then I want to know the value of x. So I want to find y of 4. So that is 30, so what is 16 plus 8 over minus 3. So that would be 16 plus 8 over minus 3. That's 24 over 3 minus 8. And y of minus 2, that's going to be 4 plus 8 over 1 plus 2, so 3, 12. 12 over 3, that's 4. Okay, so minus 2, 4, 2, 3, 4, that's looks like a minimum point. And 4 minus 8, 1, 2, 3, 4, so it's going to be very low. It's probably a minimum or a maximum point. So that's a max. That's a min. How do I know it's a max and min? Well, I can take the second derivative, for instance. But here I can guess from the asymptotes, because I do have the asymptotes. So it's not very great, so I'm just going to redraw this and say, okay, so I have an asymptote like this. I have an asymptote like this. I have a point 4 minus 8, 4 minus 8. And I have a point minus 2, 4. And the graph goes like this. Sorry, it's supposed to be a minimum. Let's check if that actually materializes. Y equals x squared plus 8 over 1 minus x. It does indeed. And we can draw the asymptotes. Y equals minus x minus 1 and x equals 1. So these are the asymptotes. Quite neat, I would say. So this is a very, as I said, it's a very typical question for an, it's a very typical question for a university interview. Let's see if I can sketch this very quickly. I'll do a really quick analysis. I won't do the whole thing. So the first thing I notice that the domain is any real number. X any real number. So I also notice that the function is odd. Odd because if I substitute minus x, it just becomes the whole thing with a minus. Okay, because y of minus x is minus x over x squared plus 4, which is minus y of x. Okay, so that's beautiful. So we just need to figure out, so the right-hand side. Now, I can see that as x becomes really big, this tends to 0. As x tends to infinity, y tends to 0. That means you have a horizontal asymptote, asymptote a y equals 0. And what else? Well, 0. There's only one 0. Y of 0 is 0, so it goes through the origin. Okay, and we want to find a maximum point, so we find the derivative, which is 1 multiplied by x squared plus 4 minus x multiplied by 2x divided by x squared plus 4 squared. So that's equal to 0. So x squared plus 4 minus 2x squared must equal to 0. X squared minus 4 equals 0. X equals plus or minus 2. These are stationary points. Stationary points. The fact that there are two of them and they are symmetrical also hints me that it is an odd graph. So we need to find y of 2 to find the value of the function at that point. 2 over 4 plus 4 equals 2 over 8 is 1/4. Finally, I would also find the second derivative and to find where the point of inflection are, but I'm not going to do this. I'm running out of time. I really need to go in a few minutes. So we know that the 0 is here. We know that this is a horizontal asymptote. And we know that this is a stationary point. So 2 and 1/4, 2 minus 2 plus 1/4. So it's going to go like this. And on the other side, it's going to be symmetrical because it is an odd graph. Minus 2 minus 1/4. It's going to go like this. And let's see if that is indeed the case. Y equals x over x squared plus 4. And indeed. One thing I have to say, I did not sketch any of these graphs before the session. I did not know how they look like. I worked it out as we went. Okay. This is the power of analyzing graphs. So yeah. So so you could see that I've made a mistake here, for example. But with the I didn't realize that there's an inflection point here. Okay. So I'll finish here. I hope this was useful. Hope you got something out of it today. And yeah, enjoy. And I'll see you. When do I see you? I'll see you in Oh, in a week's time, apparently. So I'll see you next week. Okay. See you all.